Welcome to this application video on derivatives. Once you finish derivatives in calculus, or at least all the rules, and you're kind of comfortable with them, you're probably going to get thrown into several applications. Now, the applications can actually become a little bit of a pain because as a student, your kind of breadth of the items that you've studied and application based kind of practice items isn't going to be that big. So in this video, what I want to do is I want to actually tackle a relatively hard problem, and it does deal with the concept of derivatives in kind of the business side of costs and revenues and profit. Now, those costs, revenues, and profit are dependent, and there's many different terms that you're going to be running into. So I'll try to explain to you before I tackle this relatively hard problem for you. The derivatives itself, so taking the derivative is going to be the easiest part actually of working with problems. It is understanding what is happening within the problem and then what do those derivatives actually mean. That's going to be the trouble maker for you. So before I dive into this cell phone company problem that is reporting about 1.5 million phones in terms of sales per quarter, and then it's giving us these crazy functions and different things in terms of trying to figure out, let us break down on the business side, all right, these sales. So basically what the revenue is, the costs, how are things, what are these business guys talking about? And then profits, and then what do those profits actually mean? Okay, so before I jump into this example, let me break this down in this way. So imagine that you have a phone like this, and you can imagine that you have any item, anything that you're selling. It can be a basketball, it can be TVs, anything. Okay. Or any service actually. So service like Netflix offers subscription-based services, or Spotify or something like that. But let's make it a little bit more concrete. So let's imagine that we have a phone. So here's your phone. Doesn't matter who's selling this, what brand it is, and so on. Now, in order to make up this phone, right, to make the phone itself, you're going to have a cost which is associated with making this phone. Now, the way that companies think is they have a cost per one item. Okay, so how much does it cost to make one phone? And that is typically called the variable cost. Now, within that variable cost, so this might be VC, you're going to be thinking about, what is in this? Maybe the raw materials that you have within making this, maybe the research that has gone into making, or designing this, shipments and so on. I'll put it said right here. Now we typically, on the calculus side, when we're applying these things, even on the business side, we may not always stress about all the different items, that go into the cost of making one phone, all right? But you can imagine, that this is just one cone and one phone, and we're calling it the variable cost to make that phone. Now, of course, if you make two phones, then it's going to be twice that cost. And if you're going to make three phones, it's going to be, 3 times that cost. It can happen that making more phones might be more costly to you per phone, or maybe it's going to be less costly to you per phone. And that is, dependent on what happens. We may not know that information. In calculus, we typically will be given this information, even in business. So for instance, to make one phone, if I go back to this example, they give us this crazy function right here that tells us what the variable cost is per one phone. And notice that it's not the same cost. It looks like it's changing, right? So as it goes in, it looks like it's some kind of a quadratic, you have a squared there term. Now, we may not know where this comes from. We don't actually care, but we do want to know what this function is. So this would have been just the variable cost per one phone that we would have. Okay, So hopefully, you can understand, now that variable cost. So when in business we say, or at least they say, it's not like I am a businessman of some kind, but when they are referring to the cost, they typically will be referring to the cost of this variable cost, which is going to be the variable cost per, so notice that this is, my X is, for the phone itself, multiplied by how many phones you're actually making. So that would have been kind of like your total cost for all the phones that you have made. And that's what the business guys are referring to in terms of cost. So this cost, so this would have been CX, typically designated in this way, and that is the cost for all the phones that you are making. The costs itself, there are different types of costs. There are also costs which are called operating costs. You have to actually rent out maybe the factories that you make. You have to maybe pay salaries to certain people. So you have an operating cost to run a company. And then you also have the cost of making the product. So this, we're going to be assuming that it is the cost of making a product. It has nothing to do, with turning on the lights, paying your salaries and so on. It is just how much do you, how much does it cost you to make that one product? All right, so that's the first thing that I wanted you to know. The second thing that I wanted you to know is that in order to, once you, make the product, and in order to make money, you of course are going to be selling this. So you're going to set some kind of a sale price for this phone, and this is going to be per one phone. So, this might be designated as SP, all right? So that's the sale price, per just the phone itself. And again, it might be some kind of a function. It may not be fixed amounts, okay? Typically it may, but it doesn't have to be. It may change the more phones you make. Maybe, the sale price will be changing. It's going to be going up or going down. We don't know. So that's the sale price. Now, don't be surprised that, you might be seeing this as just simply P, which is just the price. This will depend on your teachers or your profs that you have. So in that, you have to be a little flexible in what variables, especially in business. It's unlike, for example, physics, where the variables are very fixed. In business, they're not always fixed. All right, so you might run into this. So this is, kind of the demand, also known as the demand function, okay? And that is, what is the price of the phone that you have? Now, if you wanted to know what the total revenue is, so revenue is basically the entire sales if you would be selling a certain amount of phones. So if you're going to be selling 100 phones, 1,000,000 phones, I don't know, but this revenue function is equal to the price, per the phone that you have, so SPX, multiplied by the number of phones that you sold. So, notice the cost is, how much does it cost per one phone multiplied by the number of phones that you sell? And then the revenue or sales is how much does it cost per one phone? And then how many phones did you actually sell? So that shouldn't be anything, crazy. And now, if you take the difference between these two, so this is actually known as the gross profit that you have. Although, unfortunately, I don't like this, but, very often in books and so on, especially in calculus, they'll just call it profit, right? There is a difference between gross profit and, for example, net profit. Net is, the ultimate how much you actually made, not only because you have costs that are associated with making the phone, but you also have the cost of running the company. And you have to take into account all of that. But on the calculus side, this gross profit, That's why it's the word gross, because it doesn't actually include, okay, or it doesn't subtract the actual operating expenses that you have, or operating costs. So within this gross profit, what it is simply your revenue minus your actual cost that you have. And that, when you subtract, is going to give you the gross profit. Or as I said, typically it will be designated as profit, okay, or simply they'll just use this with a capital P instead of a small p to designate what the gross profit is. I'll try to talk about gross profit, okay, because there's still operating expenses to be worried about, which they do not typically cover, okay, directly. So, in summary, okay, if you're going to make an item, it's going to cost you, okay, and it's going to cost you for every single item that you make. If you want to know what the total manufacturing costs are, okay, of making that particular item, then you're going to have to take what it is per each individual item, how much does it cost, and you're going to have to multiply it by how many you actually made. If you want the total revenue from the sales, it's going to be how much are you getting per one multiplied by how many you have sold. If you want to know what the profit or the gross profit is based on these, you simply subtract the two, and then you get what the profit in between is. So that is the introduction to this. Now let's try to take all of this and tackle, this mighty problem that we have in here. So to break this down, we have a cell phone company, okay, which is reporting a steady sale of 1.5 million phones in a quarter. So they're selling quite a lot of phones. Now, by the way, if you're talking about Apple or something like that, they sell much more than that. Okay. Now, of course, it will depend on the quarter. Now, a quarter means 3-month period. So within 3 months, they're selling 1.5 million phones. Now, the present sales price per each phone is $650. So for that 1.5 million phones, we know that they are receiving $650 in sales. Okay. Now, I'm going to start writing this down as kind of a set of givens for myself within here. So what do I know? Well, I know that they have sold 1.5 million phones. Okay, this is in a quarter. Okay, so that's how many phones are sold. I know that the price, okay, if they sell this much, is $650, okay, per phone. So that would have been my sale price, okay, at that volume, at the 1.5 million. Now, the present sales, the company wants to increase the price of the phone, but a study shows that each $10 increase in price will result in a 2% drop in sales. And now this information is now, it breaks things down for us, okay? Because this tells us that, this 650 isn't fixed. Right? It depends if they're going to be increasing or decreasing the prices. So how do you model something like this? Right? So how do you model something like this? All right. So in order to model these, okay, in terms of the price, because the sales price is the following. So the sales price, okay, and now this is going to be dependent on, I'm going to put that in just a moment. It is equal. Currently, it is $650 when we sell this much. However, notice that it says that there is a 10% increase in price will result in a 2% drop in sales. So for each $10 that they increase the price, okay, now I'm going to multiply this by N, okay, so this is going to be N, where this N is equal to, okay, 1 increase in price, so one $10, or maybe 2 increases in price, or 3 increases in price, and so on. So every time I do an increase in price, all right, the actual sales price will now change. Now, this is not what we want, right? But just a moment, okay? Now, it says that the increases in prices drop a 2% drop in sales. So 2% drop in sales. All right. So that means that my X, so the number of sales, okay, so this is how many items. Okay, so the number of items currently is 1.5 million, right? That's how many we have. Now it's going to have a decrease of 2%, all right? So now 2% of this. So now what is 2% of that? So it drops it every time I do an increase in price. So it drops another 2%, okay? And so on. So in order to model this, this is going to be 0.02 times the 1.5 million. Okay, so that's 1, 2, 3. So that's a 2% drop for every time that I increase that. Now, of course, I can obtain what that is. Okay, so 0.02. Okay, so this is, moving this over. So this would have been, I guess, 1, 2. So that's 15,000. So that's 30,000. All right, so X is equal to 1500, 1, 2, 3 minus 30,000, 1, 2, 3, N. So that is the volume drop every time I increase the price. All right, that's what this information right here that I just highlighted gives us. Okay, so that's what it is. Now, we of course, because we want our sale price in terms of X, we can rearrange this equation and then we can substitute for N to get the equation for the sale price. So we can do that. Okay, so we'll do that in just a moment. So I hope that this made sense to you. Now, let me just double check. I never really trust myself when there's too many zeros. So I'm just going to punch this in. All right, so it was 30,000. Okay, so now the variable cost per phone, so they give that to us right here. Super ugly. Negative 2.34 times 10 to the negative 10. So that's a puny number. And then in brackets, X minus 0.8 million squared plus 400. So this is a quadratic function, right? So it looks like it's some quadratic function that we have. Now, they do also mention that I have a capacity that in each quarter, basically what this is saying is capacity means what is the maximum number of units that you can sell. So it's telling me 1.55 million. So we're basically at the peak here, right? So we are very close to the peak. We don't have a lot of room to make more phones. That's fine. And now let's take a look and see what they're going to be asking me. In part A, so that's the first item, find the sales price demand function. Okay. The sales price, okay, or the demand function, so that is just this SP. Again, please remember that they might use P, right? In calculus sometimes, or in business, they'll just use P. I like to use SP for sales price. So I do want this function, so I'm going to, now this is part A. So I'm going to take this, I'll rearrange this for X, so, for N. So that's going to be X minus 1.5 million. Then this is going to be that. And sorry, if I swing this over, let me just go back in here. I want to isolate for this N actually. So this is going to be, so 30,000, I'm going to bring this over to this side and I'll do the opposite. So this X I'll bring over to this side, that I'll bring over to that side. So I'm going to have this. So N is equal to 1500, minus X all over 30,000. Okay, so it's a little bit annoying, but so be it. Now let me just add a page here so that I have space to work. So now my SP, And now my n, so I'm going to now make it in terms of x, okay, because I'm going to substitute, okay, this into the equation. So I'm going to substitute it into here. So now it's going to be in terms of x. So that is going to be 650 plus, okay, 10, and then n, which is 1500, 1, 2, 3, minus x, all over, this is going to be 30,000. Okay, so now massaging this out. So this 10, okay, it's going to take out one of these. Okay, so this is what I'm going to have. So it's going to be 650 plus, I'll just leave it the way that it is, which is going to be 1500, 1, 2, 3 minus x, except now it's 3,000 in the denominator, because that 10 canceled it out. So let me do that. This is actually nothing else but just simply a line, right? So if I would do this throughout, okay, and then simplify, actually I will simplify it just to make my life a little bit easier. So let me do that in quick fashion here. All right, so there you have it. Okay, so that is my demand function, which is really just the sales price. So we can substitute now for x, you know, so 1, 2, 3, 4, whatever it might be. Okay, and then we're going to find out what the actual price is within here. Okay, so that's what would be happening within here. And notice that, you know, when x is, you know, if we substitute basically, although x can't be really 0, okay, in terms of, because then we're not really selling anything, but, you know, the original kind of sale price envisioned is 1150, okay, which is actually quite a bit. Okay, so now with this, so that would have been part A, okay, so nothing major in terms of calculus here as of yet, okay, and now part B. Okay, so find the total revenue function. Okay, so well, the total revenue function, so if you recall, it is nothing else but simply this right here. So we're just going to be multiplying, so my revenue function in here. Okay, so this is for part B. My revenue function is nothing else but this multiplied by x. Okay, so if I would do that, this is going to be 1150x minus 1 over 3000 x squared. So this is now a quadratic function. So that's going to be my revenue. All right. Now let's see what else. So now that I have that, okay, now they move over next. Now they start introducing this. Find the marginal revenue function and its value when sales are 1 million units. Okay, so for this, let me go back in here. So what we have is, or at least what we have described, we said we have a cost function, we have a revenue function, and then we have a gross profit function. Okay, now when you're studying calculus, and you know that you can take the derivative of all of these. So we can get the derivatives right here. Now, in business, when we take the derivative of the cost function, okay, we actually, instead of using the word derivative, we use the word marginal. Marginal because it is a change per unit. So marginal cost function. This would have been marginal revenue function. And this would have been marginal profit function. So marginal profit. So the word marginal refers to actually the derivative. And if you remember, the derivative is simply the rate of change. So here, if you're thinking about the rate of change, what this means is it is the rate of change of your cost function. So, you know, if you find and you take the derivative and it's positive, that means that your rate of change, that means your costs are going up per unit, right? If your rate of change for the cost is negative, that means your costs per unit are going down. If your revenue, okay, derivative is positive, again, so if it's positive, then that means that your revenues are increasing. If it's negative, your revenues are decreasing. This is per unit, okay? And then the profit the same. So it's either increasing or decreasing per unit. Now, all of these, because you're taking it with respect to X. So don't forget that the marginal cost means dollars per unit as the actual, now per unit, per item. Okay, so it is the cost per item. So how is it changing? Your marginal revenue, it is the revenue or the sales per item. Okay, so how is that changing? And then the profit is the same. It's per item, per one. That's what these marginal mean. So if in here, in the example, if they're asking us, what is the marginal revenue function and its value when sales are 1 million, what they're really asking us, they're asking us, well, take the derivative here. So we can certainly do that. That's not a big problem. This is very easy to take the derivative, right? So this is going to be that minus 2 over 3,000 x. So this is just a straight line right here. That is the marginal derivative. Now, they are asking us when the sales are 1 million. So within here, we have to substitute 1 million into this function, and we're going to find out exactly. Okay, so within here, so 1 million, 1, 2, 3, and we're going to know exactly how these are changing. Okay, so how our revenues are changing. Okay, and so within here, let me just cancel 1, 2, 3, 1, 2, 3. So this is going to be, actually this is what, 2, and let's just plug it in instead of doing all this math. So 1150 minus, and this is going to be what, 2,000 all over 3. All right, so this is what we would have. So this is 483.33 dollars, okay, per item change. Okay, so my revenue is growing, okay, is at $483.33, okay, every item, okay, that I have. Now, if you recall, let me just, I'm going to bring in decimals in here for us. Okay, so decimals calculator, let us put it in. So we have our revenue function. So let's say within here, I'm going to try our x equals, and this was 1150x minus 1 over 3,000 x squared. Now, of course, this is going to be some chaotic function. So within here, all right, and I guess because it's x squared, okay, so we have to be careful. We have to set guidelines. So I'm going to just assume x is greater than 0 because for 1 or more. Okay, so this is what we would have. And now, if I start doing this, okay, let me blow this up. All right, so there you have it. Okay, notice that it's 1 times 10 to the 9, which is billion. So that is the billion. All right, so that's what we have. And notice that it is kind of peaking. Now, we do have a capacity here, so we have to be careful. So this actually is, X, and we had a capacity of 1.55, I believe, 1.55 million units. So 5 within here, 1.55 and 1, 2, 3. All right, so this is my revenue function. So it looks like, yes, indeed, okay, it looks like it's growing. But notice it's starting to fade, right? So it kind of takes off, but now it's starting to fade. And indeed, if we had a bigger capacity, our revenues actually would have started to slowly start to drop down, because I guess the costs, okay, would have been, too heavy in order to, to keep going. So, sorry. Your revenues, okay, are going up up to that point, but it looks, because it's quadratic, it looks like it would have been fading away, right, as the units go on. So you still have a revenue, but it's not, okay, as big, so you can actually make more money selling less, okay, than more. If we actually, you know, allow this to continue, you know, let's say if this was capacity of this, notice what happens in here. Now we're going to start dropping off our revenues. Although we sell more, we don't make as much. All right, and that is because of the fact that within here we have this increase of price that we're playing around with. That's where that comes from, because that, you know, for every $10 we have a drop in sales, and that's why our revenues might start going down. So it looks like we kind of peak out. This is kind of our peak right there, which is 1.725 million units, you know, although our capacity technically is only 1.55. So that's something to think about, and this is an amazing question with regards to that. So that is now this. Now my marginal item, you can certainly graph that. I'm not going to graph it on this because the scale is so much different. You know, 483.33 would have been your marginal cost per unit that you have in there. Let me get this out of the way. Now, what else do they ask us in this question? So this is what we had. Now, find the maximum variable cost per phone. Okay, find the maximum variable cost per phone. All right, well, here's the variable cost. So what I'm going to do is, let me clean this off right here. I'll try to copy it down. Actually, let me see if I can copy this, bring it down, provide another page, close this, so paste it. So here is my variable cost. Now I want to find the maximum. So this is going to be some kind of a quadratic. Now, by the way, this is in vertex form. So if you remember quadratics, okay, and parabolas and how to graph them, notice this is like your A that you have. So notice it's going to be, you know, down. It's going to be pointing down. And then it looks like my vertex is right here. Okay, so here, my vertex looks like it's 0.8 million, okay, and 400. So it looks like that is the peak that I would have. So because this is in vertex form, answering this question is actually rather simple. If this was not in vertex form, how would you do that, right? How would you find the peak? Well, it is a parabola. So in order to do that, remember that at the peak, okay, this goes back to derivatives. You can take the derivative of this. So if you take the derivative of this and you find when this is equal to 0, you will find exactly, because the slope is 0. So that means this parabola goes up and then starts coming down somehow. So you're going to have a peak where your slope is 0. Now, because it's in vertex form, actually, I already can see it. So this looks like this will be the vertex. So that is the peak. All right. So that's going to be at 0.8 million. So about 800,000 units. Okay. And then the cost is 400. That's the maximum. But if this was not in vertex form, then I could just simply take this and then, okay, take the derivative. So that's going to be, so 2, so I'm going to bring that 2 down. So 2 times negative 2.34 times 10 minus 10. All right, and this is going to be now x minus 0.8 million. Now, notice we do need the actual chain rule here, but inside of the bracket it's just x, so the derivative of x is just 1. So that's no problem. The derivative of the 400 is 0. So really, this is what we have as our derivative. Now, since we want it equal to 0, then this actual term will drop off exactly out of the way, because you're going to have 0 equals to all of this junk right here. Let's call this a, okay, times x minus 0.8 million. Now, dividing both sides by this, okay, doesn't change anything. So that means, there you go, okay, we have the slope equal to 0 at x equal to 0.8 million. That's what this is. And if you substitute that in there, into this equation, your answer is going to be 400. Okay, so that's how we would have used it, because I know that it's a quadratic, okay, and that's what we would have. And I would encourage you, you can take it on Desmos, you know, you can clean up and then plot this out for yourself, and then you can see that it is a parabola again, and then we do have a peak. All right, so that was part number D. Part number E. So for this one, for part number E, we have the total cost is, they tell us that the total cost is 1 million. Let me copy this down in here. So it's 1 million plus the variable cost times X. Okay. So in this case, the cost is, so they're adding something in front in here. All right. Now, this is the actual cost, I guess, of making the phone. Maybe this is some additional cost, okay, that they are inputting in. Okay, so if that is the actual total cost, okay, so the total cost is, I guess they're asking us to try to find that equation. So within that, so if I substitute this back in here, let me paste it. What is that total cost? Well, so this is nothing else but just that 1 million plus the variable cost. So I would have to substitute that in. So that is negative 2.34 times 10 to the minus 10. All right, so x minus 0.8 million squared plus 400. And then all of this is multiplied by x. Okay, so I'll put the x in front there instead of in the back, so plus x. And that would have been my cost function in here. Okay, so that's what I have. Now, if I keep going, so this would have been part F. What is the profit when sales are at capacity of 1.55 million units sold? All right, well, we know the revenue. So here's a revenue function. So here it is. That's my revenue function right here. So I'm going to copy this. So this would have been, now we want to know what the profit is. It is equal to revenue minus, so all of this minus, okay, all of this. So I have to get all of this junk right here. So copy, paste. Okay, so that is the total cost that I have. And now they're asking me, so within here, at 1.55 million, so what would the profit be? So I have to substitute into here 155 million to find that out. So let me do that in fast forward fashion. All I'm going to do is just substitute this whole thing in. All right, so you have, so here's your total revenue, here's your total cost, and now if you subtract the two, you're going to get your profit. Okay, so within here. So there you have it. So you can take that in and do that substitution. So 981,666,666.67 minus 416,981,250. Okay, so we have approximately 564, point, I'm going to round this, 0.7, and this would have been $1 million of gross profit. So pretty crazy, okay, for that. And so now I think that finishes it off. What is the marginal profit? So here the marginal profit at 0.5 units sold. And then what does it mean? Well, marginal profit means we have to now take these. Okay, so this is pretty mean. We have to take this functions. Okay, so we have to take this minus this, and then find the derivative of that, and then substitute. Okay, so within there, we'll be substituting, I guess, at 0.5, so at 500,000 units. Okay, so that's what we would do there. Okay, so for that one, again, let me do that in fast forward fashion for you. So I'm going to take the derivatives of those and then see what happens. All right, so that is the derivative. So that's the marginal profit. And now substituting, so within here, we would have to substitute the 500,000 and then find out what the answer actually would be. All right, okay, so that took a while, but I also wanted to show you. So what I ended up doing was I actually plotted on decimals the revenue, the cost, the profit. So as you can see there, you can also see that you can take the derivatives by just taking the prime. So if you're looking on the left-hand side on decimals, you have all of the values. So I actually did all of that and then calculated it all. And then on the left-hand side, I took the derivative and then just substituted everything back in. So the marginal profit is 367.53 cents per item. And if you're looking on decimals on the right hand side, you know, so you can see the revenue is actually the red that you have. The blue, the one all the way at the bottom, is actually the cost function. And then the purple, so the one in the middle, is actually your profit. So you'll see that the derivative of the profit is always positive, actually. Well, at least for between 0 and the capacity of 1.55 million. So this is pretty neat. You know, I would encourage you to try it. Okay, so as you're going through all of these, you know, you can utilize decimals to visualize a lot of these things. This was a super, super hard question. If you grind it out through the whole thing, the extremely long video, congrats to you. We'll see you in a future video. Okay, happy studying calculus. Bye, everybody.